Thanks to the organizers for inviting me, and thanks for all of you for showing up. I'll talk about something that Borna's talk is a good lead up to. The first thing I'll of course do is violate her advice on the last slide. So there will be no networks. All machines will be independent. And I've lost my slides. Okay, let's step on this. So this is joint work. This comprises two different projects. This is like all the people involved in these projects include Sungjin Aim, who used to be a postdoc at Duke, has since moved to UC Merced. Nat Kell, who is my student, and he is here. Nat is responsible for the slides, so if you like them, he's the person to talk to. Janardhan Kulkarni, who was a student at Duke and is on his way to UMN via Microsoft Research. Janardhan is also here somewhere, probably not in the room. And Mariam Shadlu, who is Sungjin's student. So what's the problem I'm going to talk about? So let me start off with a very classical question, something that's been studied for a very long time. And this is online load balancing. In fact, if I'm not mistaken, this is the first online problem that was considered in computer science. So the problem is the following. It was considered by Graham in the mid-60s. You have a bunch of jobs. Every job has a processing time. You have a bunch of machines. Let's imagine for now that the machines are all identical. And the question is, how do I assign the jobs to machines? So let's say I assign the first job to the first machine, second job to the second one, third job to the first machine, and so on. I keep assigning these jobs to machines. The load on a machine is simply the sum of processing times of the jobs that I assign to the machine. So this is the completion time of the machine, if you will. Okay, the time by which it finishes all the jobs assigned to it. And our goal is to minimize. Before that, the problem is online, which means that I don't get to see the future. I get a job, I see its length, I need to assign it. I don't know what's coming in the future. And the goal typically is to minimize the make span. And this is again something that Borna defined. It's simply the maximum load. You look at all the machines, whichever has the maximum load, that's the make span of the schedule. And throughout the talk, I'll measure the performance of an algorithm via the standard notion of a competitive ratio. So the competitive ratio is simply the ratio between the make span or whatever objective I'm considering produced by the online algorithm, by my algorithm, and the optimal make span. Of course, the optimal solution is completely offline, so it knows the entire instance it assigns in an optimal manner. Okay, so that's the online load balancing problem. And of course, over the last 50 years or so, a lot of variants of this problem have been considered, and we'll touch on some of these. So in particular, there have been two directions in which the problem has been generalized. The first is that objectives other than make span have been considered. In particular, the so-called P norms of machine loads have been considered. I won't actually define what P norms are, but just as a simple example, the one norm of machine loads is simply the sum of all the loads. Okay, instead of taking the max, you take the sum. So you can think of other P norms as some kind of somewhere between the average load and the maximum load. These two are the extremes. Okay, the max load is the infinity norm. So various P norms have been considered. Also, various different machine models have been considered. So when I was introducing the problem, I said that all the machines are identical. In this case, the load of a job is simply defined by the job itself. So I'll denote the load simply by P sub j. But there are other models, for example, related machines. This is something Borna also mentioned. In related machines, every machine has a speed. The speeds are not necessarily equal. So machines have non-uniform speeds. And the load of a job on a machine is simply the ratio of its processing volume and the speed of the machine that it's assigned to. And then there's unrelated machines, again something she mentioned, where every machine job pair can declare its own load. Okay, so the load of a particular job machine pair has nothing to do with the load of a different job machine pair. So of course, unrelated machines are more general than related machines, and related machines are more general than identical machines. So as we go down this list, our results will keep becoming weaker. Okay, and as this slide attests to, this problem is very well studied. So I'm not going to actually talk about this problem per se, but I'm going to ask the following question. So how do we load balance simultaneously if we have multiple resources? So what I was showing you earlier had just one resource, let's say processing time. And we have various algorithms to balance the load on multiple machines if we have just one resource. But let's say in a data center environment, we have many resources, maybe processing time, like CPU time, and storage. If we have two different resources, how do I simultaneously load balance on two resources? Okay, so that's the question that I'm going to address in this talk today. So to make this formal, we'll call this problem the vector scheduling problem. In particular, again, I'll talk about the online version of the problem. So it's online vector scheduling. So now my jobs are vectors. Okay, every job has a resource has a requirement defined for each resource. In this example, I have three different resources. So there's a blue resource, a brown resource, and a green resource, and every job declares a certain requirement for each of these resources. And as usual, I have to assign the jobs to machines. Every machine also provides all these resources. So each machine has three resources here. And when I assign a job to a machine, it produces the corresponding load on each of the resources.
Just
show on this point whether the resources are per machine or global.
No, so per machine.
Per machine.
Yeah. So for now, all my machines though are identical. The machines are exactly identical. There's no difference between the machines. It's just copies of each other. Okay. So when I assign a job to a machine, it produces a load on each of these dimensions. I'll also call these dimensions or resources. And as usual, I ask the same question. I keep assigning these jobs. Loads accumulate on the different dimensions. And what I want to do is to minimize the maximum load that I accumulate. Okay. So in particular, I'll now define the make span of this multidimensional schedule as the maximum over the make spans in the individual dimensions. So I don't want any of these resources to be poorly load balanced. Okay, so that's my definition of make span. Similarly, I can define all kinds of p norms. So again, I'll take the maximum across all dimensions, but now in each individual dimension, instead of taking the infinity norm or make span, I can take whatever norm I wish. And the norms need not be identical. The norms could be different. So maybe on the first resource, the right norm to look at is the 2 norm. The second one, maybe the L5 norm is the right one, and so on. Okay, and in fact, a lot of work in the 70s in the systems community actually tried to nail the right norm for different kinds of resources. For example, I think the general consensus was that for storage or hard disks, the right resource to look at, or the right norm to look at, is the L2 norm. There were other different resources that people came up with various norms for. Okay, so that's my problem. I am getting jobs online. I have to assign. Jobs are vectors. I have to assign these vectors on machines. For now, imagine that machines are identical. How do I assign it to minimize either the make span or some other p norm? Okay, so here's a very quick summary slide of the kinds of results that I'll talk about. I clearly won't talk about all of these results. As I said, there are two different projects that I hope to say a few words about. The first one is something that we did a couple of years ago. And this looked at identical machines, the case of identical machines and the case of unrelated machines. So the two extremes. Okay, and the main, basically, if you look at all the results, basically what we did was we closed the problem both for make span and any arbitrary p norm minimization. So all these thetas, wherever I've written a theta, it just means that we give matching upper and lower bounds. Okay, so we give an algorithm that achieves this bound, and we show that you can't do better. I won't talk about all of these. The only one I want to talk about today is just this one result. So this is the simplest version. All my machines are identical. I get these vector jobs. I want to assign the vector jobs to minimize the make span. Again, what's the make span? Maximum load across dimensions and machines. Just the maximum across all of these boxes. Is the problem clear? Any questions about the problem? Okay. So let's first look at an algorithm for this problem. And contrary to some of the previous talks, here for this particular result, the algorithm will be very simple. Showing that that algorithm is the best will be a little more involved. Okay, so let's start off with what is perhaps the most obvious algorithm you would try to use, which is the greedy algorithm. Well, I get a vector job. What do? I simply try to assign it to the machine where the maximum load it causes on a dimension is minimized. That's perhaps the most natural strategy you can think of. Now, of course, this strategy has an obvious problem, which is that it's only looking at the maximum dimension and it's ignoring everything else. Okay? In fact, this leads to unbalanced loads on dimensions. What tends to happen is you can create sort of pathological instances where the loads on different dimensions will become extremely unbalanced, and the competitive ratio, the quality of the solution, can suffer. In fact, the competitive ratio can be as bad as polynomial in D, okay, something like square root of D. So this is not so great. We would want competitive ratios that are better, things like logarithmic in D. So maybe greedy is not so good. What's the next algorithm we would try? Well, the next obvious algorithm, just throw the jobs at random, right? Take every job, send it to a random machine. This is better. So if I send every job to a random machine, just by simple Chernoff bounds, so note that I have D dimensions and M machines. So I have dm boxes here. So if I use simple Chernoff bounds, it's easy to see that with high probability I won't go over a load of log dm. Okay, assume that the optimal load is 1. So this gives an immediate log dm competitive algorithm. In fact, this is optimal if you have unrelated machines. Okay, now for unrelated machines you should not throw it randomly. Of course, the machines are different. You need to use a different algorithm. But for unrelated machines, this factor is the best you can do. But for related machines, for identical machines, this is not very satisfactory, because think of the two terms here. D is the number of dimensions. This is small. This is typically going to be pretty small. M is the number of machines or racks or clusters. This is going to be really large. So I don't want a dependence on M if I can help it. And the first algorithm, the greedy algorithm, that was terrible in terms of D, but that did not have a dependence on M in its competitive ratio. Yeah. So the natural question to ask is, can I combine the benefits of the two? Okay, can I retain the log D here, the dependence of D to be logarithmic, but can I get rid of my dependence on the number of machines? And indeed, that can be done, and we do it using a very simple algorithm. So here's this algorithm. So it's almost exactly the random algorithm. So you just assign every job uniformly at random on the machines, except that in every machine you draw a line at this number log D over log D. Okay, so that's the target competitive ratio that I am hoping for. I want to keep my make span down to log D over log D. Everything here is scaled so that opt is 1. Okay, so I want to keep everything down to log D over log D. Was there a question? No. Sorry. So now, as I keep throwing these jobs randomly, what will happen is that this bound that I'm trying to maintain will be violated. So for example, if this job gets assigned to the first machine, maybe the job exceeds this threshold. So what do? Well, I simply take that job off, and I create a second copy of all the machines. And now, instead of using the random algorithm, I use a greedy algorithm to assign the job. So I now have 2M machines, but I claim that now I have actually created a load that cannot be more than log D over log D. Why? Because by simple Chernoff bounds, how much of my volume will get transferred to my second round? Only about 1 over polynomial of D of the volume, right? Because the probability that I'll overshoot will be about 1 over poly D. And now if my volume shrinks by 1 over poly D, I've basically gotten down to a one-dimensional problem. So now I can use a greedy assignment, and I would be fine. Okay? But now I have, just 1 minute, I have 2M machines. I had just M machines to start with. So what do? I just come up with a matching on these machines and merge them. My loads just go up by a factor of 2. Okay, so that's the simple algorithm to get this log d over log d factor. Yeah.
Do you assume you know the value of the optimal?
Yeah, you can guess that. You can keep guessing, and since it's online, you can keep updating your guess. Okay, you can use there's a standard doubling trick that you can do. Okay, so is the algorithm clear to everybody? Okay. The more interesting question is this the best we can do? And perhaps surprisingly, it turns out that it is. We can't actually do anything better than this very simple algorithm. And I'll tell you a little bit about why that is the case. So we'll show that we'll first construct a coloring problem, an online coloring problem on graphs, and use that to show that this log d over log d lower bound for vector scheduling is in fact optimal. Okay, so let me switch from a scheduling to graph coloring, and then we'll see why these are connected. So what's the graph coloring problem I'm interested in? This problem is what we call online monochromatic clique. So what's the problem? I have a graph. I give you a fixed number of colors. Let's say I have a graph, I give you 5 colors. I ask you to color the graph, the vertices of the graph, using these 5 colors, such that the size of the largest monochromatic clique is minimized. So typically in graph coloring, I don't give you a fixed number of colors. I ask you to minimize the number of colors such that there is no monochromatic clique, right? The graph is properly colored. Here I'm giving you a fixed number of colors, but I want you to have the smallest monochromatic clique that's possible in the graph. Okay? And it's online because I will give you the vertices one after another. I won't tell you the whole graph up front. I give you one vertex. You have to, let's say I have given you 3 colors, red, blue, and green. I give you vertex 1. You color it, let's say, using green. Now I give you vertex 2. I tell you the adjacencies between vertex 2 and 1. You have to use a color to color it. And I keep going. I give you vertex 3. You need to color it. Vertex 4. You need to color it, and so on. Okay? So this is, let's say you come up with this coloring. At this point, the value of the objective, the largest monochromatic clique in this graph, is 2, because there is an edge between the 2 green vertices. Okay? And you want to minimize this as the game goes on. So here are 2 instances, the same graph. There are 2 different colorings. The one on the left is a pretty bad coloring. There's a monochromatic clique of size 5 here. The one on the right is pretty good. In fact, this is the perfect coloring. Okay, so the objective is just 1.
Edge between 2.
Oh, it's not. Yeah, it's not a perfect coloring. There's an edge between the 2 reds. So it's So it's 2. Sorry. Oh, good catch. Okay. So this, for this problem, I want to show that this problem has a lower bound. So you can't solve this problem well. Okay, so here's my construction of the lower bound. So the lower bound, I'll describe the lower bound in terms of a game. This will be a game between the adversary, that is us, the one I am trying to create my lower bound. I'll call myself the adversary, and the online algorithm that's trying to beat this lower bound. Okay, so there's an algorithm, there's an adversary. We don't think of us as adversaries, but for the sake of this construction, please think of yourself as an adversary. Okay, now this game, in every step of the game, there will be 3 steps. In the first step, the adversary will give a vertex and define the adjacencies with the previous vertices. So that's step 1. So for instance, let's say I had these 2 vertices earlier. I give you a 3rd vertex, and I define what edges this 3rd vertex has with the previous vertices. Now the algorithm colors this vertex. That's step 2. To distinguish between what the algorithm is doing and what an optimal solution is doing, I'll use the algorithm's coloring. I'll call the algorithm's coloring as placing vertices in bins. Okay, so here I have 4 colors. The algorithm has 4 bins, bins 1 through 4, and the colors are what the optimal solution uses. So I'll have 4 colors for the optimal solution, 4 colors for the algorithm. To distinguish between the 2, I'll call the algorithm's colors as bins. Okay? So the algorithm places this vertex, let's say, in bin 3. Okay? That just means algorithm uses color number 3 to color it. And now step 3 is the optimal solution. It comes in and colors this vertex using a color. So this game will go on, and I'll show in this game that you will get to a situation. I'll force you into a situation. For any algorithm, I'll force it into a situation where it produces a monochromatic clique of size square root t, where t is the number of colors, the palette that I gave you, whereas the optimal solution will only have a monochromatic clique of constant size. Okay, this is the overall goal. Okay, so how do we go about doing this? We take every bin and split it up into square root t slots. Okay, so again, the algorithm had t bins. There were t colors given to the algorithm. Each bin, I'll think of each bin as split up into square root of t slots. So here I have 16 colors. The algorithm has 16 bins. Every bin is split into 4 slots. Okay, what are these slots? So we will associate with every slot a distinct set of square root t colors. Remember, there are square root t slots, the total of t colors. So I'll just take my t colors, partitioned into square root t parts. So here I had 16 colors. I have partitioned into 4 color groups of 4 colors each. Associate each slot with a unique set of 4 colors. First slot has these 4 colors, second slot has the next 4 colors, and so on. Okay, this is just for bookkeeping. Okay, I have bins which are split into slots. Every slot is associated with a bunch of colors, unique colors. Now I'll use a code in my construction. Just think of a code as a sequence of strings. Each string will be of length t and will be drawn from a root t sized alphabet. Every character of the string will be drawn from an alphabet of size root t. Okay. So now, how does the adversary define a new vertex? The way it defines, let's say it has to define the ith vertex. What does it do? It looks at the ith string in the code. The code is a sequence of strings. It looks at the ith string. What's the ith string? It's a string of length t where every character is from a root t sized alphabet. So if t is 16, if there are 16 colors in the game, it's a string of size 16 where every character is either 1, 2, 3, or 4. Okay, so it's a string like that. So it looks at the ith string, and now it connects the new vertex to all vertices that are sitting in slot 1 of bin 1, because the first character is 1 in that string, slot 3 of bin 2, because the second character is 3, and so on. Okay, slot 1 of bin 3, and so on. It looks at this string and it defines adjacencies accordingly. So here's an example. Here I have a string. So just look at the first character here. The first character is 1. What does that indicate? Go to bin 1, look at whoever is sitting in slot 1 of bin 1. I will connect this vertex to both of those vertices that are sitting in slot 1 of bin 1. Okay, and I keep doing it for all of the bins according to this code word, according to this string. Okay, so that's how I define my adjacencies. That's step 1 of my construction. What's step 2? In step 2, the algorithm comes in and says that, okay, this is a vertex I place in a particular bin. That's the algorithm's coloring. Just places it in a bin. If it places it in let's say bin 2, then I say that for the purposes of my bookkeeping, I say that it's placed it in slot 3 of bin 2. Where did I get slot 3 of bin 2? Go back to the code. In the second position of the code, I had 3 there. So I'll say that it's placed the vertex in slot 3 of bin 2. So again, look at this case. Here was my vertex. The algorithm decides to place it in one of the bins. Okay, it's placed it in bin 15. Now, since the 15th character is 3, I say it's in slot 3 of bin 15. Okay, so that's where I take this vertex and place it. So this is step 2. Algorithm has played its hand. Now, finally, my optimal solution needs to play its hand. So now the optimal solution does something very simple. It goes into the slot where I placed this vertex, and it uses an unused color in that slot. Remember, every slot has root t colors. it looks at all the colors that have been used already, takes one color that hasn't been used, and uses that to color the vertex. In this case, I am in slot 3. It goes into slot 3. It could have used pink, black, or green. Okay, let's say it just uses black. So that's the entire game. Those are the 3 stages. And this game continues. When do we stop? We stop the moment I see a slot with root T vertices. Note that at this point I have to stop, because otherwise at this point all the colors have been used up. If I still keep adding vertices, I won't have a new color to color it by. Okay? So the moment one of these bins has 4 colors in this example, I'll say I'm done. That's the end of the that's the end of my construction. Okay, so that's the entire construction. Any questions about the construction? Okay, so what are the properties of this construction? The first obvious property is that the algorithm has been forced to create a monochromatic root T clique. Why? Because one of my slots has root T vertices, and every slot has a complete clique, has a complete graph. It's a clique, right? That's how I've been constructing my instance. So the algorithm has been forced to create a monochromatic clique of size T. What about the optimal solution? Well, inside a bin, the optimal solution has perfectly colored the vertices, because it's coloring every vertex with an unused color. So the only way an optimal solution can be creating monochromatic cliques is across different bins. Inside a bin, optimal solution is perfect. So the final thing, and this is something I won't show, is using the probabilistic method, we can show that there exist codes, these strings, such that the optimal solution only creates constant size monochromatic cliques. Okay, this needs a proof, and I'm not going to show it. But once I have shown that, that means that there is a square root T lower bound for this problem, because the algorithm has a root T clique. Opt does not have a root T clique, just has a constant clique. So so the gap between the algorithm and opt is root T. Okay, so that's the first thing that we show. But now, why is this useful? What has all this got to do with scheduling? Yeah.
So it's maybe before you move on. So this is a lower bound against adversaries who know random bits of the algorithm.
This is a lower bound against deterministic algorithms.
Right. But the algorithm that you're using for vector scheduling in the end is randomized, right? It's randomized.
No, so that can be de-randomized. The randomization is not crucial.
Is it plausible that you can do better with randomized algorithms?
It's unlikely, I would think, but this I don't have a lower bound for randomized algorithms. Okay. So how does this relate to scheduling? So here's how we translate this lower bound into a scheduling lower bound. So I'll use M machines. Machines will correspond to colors in my problem. Yes, jobs will correspond to vertices. Remember, vertices were being colored. In the scheduling problem, jobs are assigned to machines. So it's natural to say that jobs are vertices and machines are colors. Dimensions will be so the number of dimensions I'll have is going to be roughly m raised to O of m. Okay, it will be m squared. That's the total number of jobs I have. Choose square root m. Okay, where m is the number of machines and m squared is the number of jobs. Every dimension will correspond to a unique subset of square root m of the vertices. So remember, there are m squared vertices. I take every subset of square root m size, and that's a dimension for me. So here, for instance, if I have if m is 9, then I have 81 vertices, and every 3 subset of 81 is a dimension for me. Now, in the coloring problem, I get a new vertex, and the vertex defines some adjacencies. How do I translate that into a new job? I need to define this vector of the job, right? The load vector of the job. The way I define it is let's say this is vertex 6. So I go in and look at all the dimensions that have the index 6 in it. Okay, all these 3 subsets that have 6 in it, and I put a 1 on the load, in the load vector on that dimension, if and only if I have a clique conforming with all the previous vertices in that set. So for example, if I go into that set 2, 3, 6, here 2, 3, and 6 form a clique. It's a triangle in the graph. So I put a 1 in that index. And I do this for all indices that satisfy this property. Okay? And if I do this, and I'm not again going into the details, it's pretty easy to see that a square root t-sized clique, monochromatic clique, will simply mean that on some dimension I get a load of square root t. Okay, so monochromatic cliques are exactly capturing loads on individual dimensions of machines. Okay, so let me move forward, and then the log d over log d bound simply comes from a calculation. So I get a square root of m bound, and then d is defined in terms of m. If you do the math, you will get a log d over log d bound. Okay, so that was this lower bound. So let me move on and talk a little bit about something that we have been doing recently. Yeah.
Just jump in again.
Yeah.
So I mean, your motivation here at the beginning was that you think d is small compared to m, right? But d is like massive compared to m.
That's right. So these results are not very practical in that sense. So these are meaningful only for asymptotic d's. If d is small, so we have some results for d equals 2 in particular, but it's very messy and it's not very clean. So
D is like log n or something like this.
right. So then it's not clear. But even for d equals 2, the optimal constants are not known. Okay, so let me talk a little bit about related machines. This is work we have been doing recently. So remember that in related machines, every machine has a speed, and you simply divide the total job volume by the speed to get the processing time. Now, in the vector case, related machines can have two possible interpretations. The first is what we call the homogeneous case. In this case, every machine has just a single speed. Okay, so machine 1 has speed 1, machine m has speed half. What that means is that if a job is assigned on a machine, it gets scaled on every dimension uniformly by the speed. Okay, so the job had these volumes, it just gets scaled uniformly. That the second job, if it's assigned to the slower machine, its volume will increase by a factor of 2 on all dimensions, but it's uniform across dimensions. So that's the homogeneous case. You can also define a heterogeneous case where you have a speed for each different resource, and these speeds need not be the same. And then again, the usual thing happens when a job is assigned to a machine. The scaling depends on the speed on that dimension. Okay, and what we show is that there is a qualitative distinction between these two cases. So it turns out that in the homogeneous case, where I had just a single speed on all dimensions, there we can match the bounds that we got for identical machines. So related machines behaves like identical machines. Related machines, of course, is more general. So here the algorithm is the interesting part. Okay, the lower bound just carries over. So the algorithm is interesting here. On the other hand, for heterogeneous speeds, we can show that the best you can do is the same as for unrelated machines. So here the lower bound is the interesting part, because if I can show a lower bound as the same as the unrelated machine, then of course the algorithm carries over from unrelated machines. Okay, so I won't go into all the details here. Let me, I should also mention that even for the classics like Graham's scheduling problem from the 60s, nothing was known for arbitrary p norms for related machines. So the only result known for related machines was for the make-span norm. P norms was completely open, and this, our result as a corollary, gives the first constant comparative algorithm for this problem. Okay, so I'll just say a few words about the main idea that goes into these results. I won't give details of the algorithm. So what would be a natural idea to try? I give you a bunch of related machines. I also have shown you an algorithm for scheduling on identical machines. Somehow you want to coerce your instance of related machines into an instance of identical machines. How would you do that? Well, one way perhaps is to say that let me take all machines of similar speeds and group those machines into groups. Okay, so I have groups of machines of speed 1, a group of machines of speed half, group of machines of speed a quarter, and so on. And now if I can somehow come up with an assignment of the jobs to these machine groups, then inside the groups I can use my identical machines algorithm. Okay, and of course these speeds need not be exactly identical. As long as the speeds are within some factor of each other, we are fine. The problem with this approach is that once I have done this grouping, imagine a situation where all my computational power is in my faster groups. So for example, here, the fast group has a computational power of 4. There are 4 machines of speed 1 each. Next one has 3 halves, and so on. So it's very heavily loaded towards the faster groups. What happens in this case is any reasonable algorithm, no matter what algorithm you come up with, any reasonable algorithm will basically push all the jobs into these faster groups, into these fast groups with high computational power, and completely ignore the slow machines. But cumulatively, the slow machines have a lot of computational power, and ignoring them hurts the algorithm badly. Okay, so this is the main sort of conceptual challenge that we run into. How do you deal with this situation? So one way to deal with this situation, it would have been nice if somehow the fast groups had smaller computational power than the slow groups. So then the slow groups would have a lot of computational power. I would have sent all my small jobs there. Fast groups have small computational power. I would have sent only the really large jobs to the fast groups. So somehow if I can ensure that my fast groups have small computational power compared to the slow groups, then maybe I can run an algorithm. So we forcibly ensure this. And we do this by a technique that we call machine smoothing. And this can be used in related machines for any problem. It's not specific to the problem that we are looking at. So what's the technique? So let's say my speed 1 machine forms the first group. It has a total power, computational power of 1. Now I keep grouping all machines. Here the numbers are not correct, but I keep grouping all machines such that I get a total computational power of 2. Okay, all the slower machines, and replace them, simulate them by machines of speed half of the right number. So there can be an arbitrary number of machines here that have very different computational powers. I take them, I replace them by a set of machines of speed half. And I keep doing this. I take a bunch of machines of total computational power 4, replace them by 16 machines, each of speed a quarter. Okay, so I'm changing my instance. I'm taking this instance of arbitrary machine speeds, transforming it into something that looks really nice. And the interesting thing that we show is that in general, if you do this, the make span does not change. So if I have a good make span on these machines, I have up to a constant factor, I have the same make span on the transformed instance, and vice versa. So these two instances are up to constants. These two instances look the same. And this is not just for the make span norm. A very similar thing holds for any norm. You give me any p norm, I can come up with a transformation. I can take any arbitrary instance, create a very nice instance out of it. It turns out that this is enough for make span. So once you have this, there's a standard technique after this point called slowest fit, which is used in one-dimensional scheduling. You simply assign to the slowest machine group that can accommodate the job. You keep doing this, and eventually, once you have assigned to the machine groups, you then distribute it among the machines using your identical machines algorithm. Unfortunately, the idea in slowest, what's the idea in slowest fit? It says that, oh, I know the optimal schedule, I know the optimal make span. Let me assign to the slowest machine group, which does not violate my competitive ratio. So let's say my opt is 100, my competitive ratio target is 2. As long as I look at all the machine groups, in whichever group in the slowest group where I don't exceed a make span of 200, I assign there. Okay, this is the idea of slowest fit. Very simple idea. Just always go to the slowest group as long as that group does not violate your desired competitive ratio. Now, unfortunately, this works very well for make span. As I said, just this idea is enough. Does not work for any other norm. Why not? Because let me tell you that the L1 norm, the optimal L1 norm is 1,000. How do you divide it among the groups? If I tell you the optimal L2 norm is 1,000, you don't know how to divide it up among the groups. There can be various different ways in which you can achieve an L2 norm of 1,000. In the actual vector loads on the groups can be very, very different. Unlike for make span, if I tell you the make span is 1,000, every group has a bound of 1,000. But that's not true of any other norm. So this slowest fit idea is very it can only be used for makespan, and that was the main reason that this problem, even for 1 dimensions, had been open for so long. So what we do for P norms is we use a very different strategy. So we use 2 interleaved algorithms. We use an algorithm that creates a fractional solution and an online rounding. The online rounding is not very complicated. It uses something like slowest fit. But the interesting one is, how do we create a good fractional solution? And it turns out that the right thing to do is to define a fractional relaxation, a suitable fractional relaxation of the LP norm. Of course, it's not a linear objective, it's a convex objective. And then on this convex objective, we define a gradient descent algorithm. Okay, so it's a continuous gradient descent algorithm on a nonlinear convex program. And that gives us a fractional algorithm, and then we can round it, and we can get a constant approximation. Okay, so I won't go into more details. That's all I have. Thank you.
Any questions?
So this sounds stupid, but I'm curious. So in this rounding scheme, why are you not using an ILP and rounding off using an LP? Why is specific?
In the last one? So, I mean, I don't know how to solve the ILP. The gradient descent is a continuous algorithm. It will only give me a fractional solution. So I have to come up with some rounding of the fractional solution that I get. It's a continuous, like it's just going with, I define some potential. Potential gives me a gradient. So I just go with that gradient in the assignment. So I'm assigning tiny bits, right? If I assign integrally, then I'll go too far down the gradient and I'll be too far off the.
Other questions? Okay, so let's thank the speakers of this session.
Thank you.